Good afternoon, everyone. Some of you might be good morning, some of you might be good evening. So today we're going to go into the next 40 minutes into the results, the findings, the methodology that we have followed and we have found as well in terms of the results uh, for this particular part of the project, which is really the impacts of electric vehicles on different types of grids. Uh, this will be presented by myself, Nando Choa, from the University of Melbourne, and also Dr. William Manson. Uh, the structure of this presentation is as follows. First, a little bit about the project Superquake, and then we're going to get a little bit more into the details of what these impacts that I'm talking about are about and what it relates to the electricity grids and the different types of grids. Then we're going to get very quickly to the modeling that we have done. We presented a little bit about this 3 months ago, more or less, with some preliminary results. And so we're going to go relatively quick on that modeling, but it's important to mention it just for you to know what are those networks that we are modeling and how we managed to model them. And then we will get into the two more important parts of this presentation, which are the actual electric vehicle modeling and the considerations. So it is a quite sophisticated modeling that has been done based on real data from an electric vehicle project from the UK. And then mixing everything together, the models of the grids, the demand, photovoltaics, where applicable, and the electric vehicles, then we move on to the impact assessment on the different grids that we have modeled. And we're going to present all those very interesting results. And finally, some key remarks. Right, let's move on. So first of all, with the electric vehicle integration project, we are going to share the slides. So there are a lot of references and links as well, so you will have access to all of that. So no worries. So first of all, right now we are in the completing the first year of the project, and this is really completing all the modeling of the distribution networks that we have been given by the corresponding companies involved in the project as well, and assessing the corresponding impacts of unmanaged electric vehicles. By unmanaged, we mean there's no management, there's no control of them apart from the people plugging them in or out from their chargers at home through the simulations, of course. And the next step, of course, is once we understand, the ability of our grids to host electric vehicles without anything clever being done there to manage electric vehicles, what is the next stage? And then we're going to get into these active management strategies later this year, and we will start presenting as well the results the next 3 and 6 months. And then we will continue with technical analysis. As part of the project, there are multiple people that you can see here. I just want to give a shout out to Jing. Jing is the person that was behind as well the electric vehicle modeling. And of course, you will have as well Will presenting part of the presentation today as well. Thank you very much to ENA and the API and C4Net, of course, for their support here. Now, let's start. So what are these impacts that we're talking about when it comes to electric vehicles and the grid? So let's start with the basic aspects here, all right? So I presented this a little bit like 3 months ago as well, but I decided to go a little bit more into details. When we design the low voltage network, which are the part of the electricity circuits that are connecting our houses, our businesses. So here in Australia, we're talking about the line-to-line voltages of 400 volts or line to neutral, for each house, single phase connections of 230 volts, right? So when we do these designs, we consider the diversity of the houses and how people are going to use electricity, the demographics. Certain places have bigger houses, or right, mansions even, and some places have really smaller houses. So we consider what it means in terms of electricity consumption as well. And we also consider demand growth. So this is done everywhere in the world, all right, with different values, with different considerations, of course, but we end up with what we call ADMDs, which is an after diversity maximum demand, which is also, in simple terms, an estimated average coincident peak demand. And we use these values to design, all right, these networks, which then determines the size of the conductors and the size of the transformers and everything, for us to be able to cope with electricity demand, particularly during the peak, all right? Now, people use their houses in different ways. Fine, but in average, in the coincident peak, not all the people are using the electricity equally. So whilst you're using a lot, your neighbor might not be using much, and then that averages out. So that average is less ADMD. That in New South Wales, for instance, is much higher than in Victoria. And in Tasmania as well is much higher than in Victoria, for instance, as well. All because of the different use of electricity. So in New South Wales, you can argue that people have many more air conditioners or even a swimming pool. In Tassie, you have more people using water heaters with electricity or more heaters in general with electricity as well. So all of these changes how we dimension these electricity networks. And this has also various impacts on the electric vehicles, all right, and the effects on the networks themselves. Now, because the solar networks have been designed for an ADMD of about 3 to 7 kilowatts per house, just the normal houses, not the mansions, right? It means that in general, considering that in practice, we're going to use a little bit less than that, all right, per house in average, because this already is considering growth and other things, there will be room for electric vehicles. And that's good news. But how much room is a big question, all right? So can we really think that everyone can have an electric vehicle and the network is going to be okay? Well, that's what we are trying to assess here, all right? Now, let's talk about electric vehicles. Now, the thing is that we have, internationally speaking, different charging types, different standards. Now, the standards that are becoming more common, and the standard from the IEC is 61851, and when we look at the single phase modes, they are called modes really in the standard. We call it here level 1 and level 2. These are charging demands that are of 3.7 for level 1 and around 7.4 kilowatts for level 2. Now, most people will not want to have level 1 chargers because, of course, it means less demand, which means longer period of time to charge your electric vehicle. And the reality is that around the world, you know, the adoption of chargers will go towards level 2, which is around 7 kilowatts, you know, if you are looking at voltage levels here, like in Australia, 230 volts line to neutral. Now, what is the problem? Well, if we have many electric vehicles, we're going to have an effect on our voltages, and the corresponding currents are going to be bigger, and then they can actually be much bigger than the corresponding assets were designed for. And the challenge really is that not everyone will, you know, charge simultaneously, all right? And we will demonstrate here through our simulations what it's going to be kind of the coincident charging. But even if it is 30% of those values, it adds, all right, as demand during the peak, and then this can have serious consequences on the networks. And if there are issues, of course, then we will have to think, okay, we need to come up with some solutions. So that's the whole point here, right? We're trying to model things in a very realistic way to understand to what extent our existing networks can actually handle electric vehicles. The next stage will be, what can we do to increase that hosting capacity? Now, it is not only related to the low voltage parts of the grids, it's also related to the corresponding high voltage. This is how it is called, the medium voltage here in Australia. We call it high voltage, 11 kV, 22 kV, for instance, all right? And the challenge here is not just, you know, that there are going to be aggregated issues as well because of all the demand that the high voltage parts are going to see. It's just the fact that we have different type of networks as well, right? So some houses are connected to what we can call, generally speaking, a rural network or an urban network. An urban network will be a smaller area, high density of houses, of course, as you would expect. That also means that the impedances, you know, generally speaking, are going to be smaller compared to the rural areas that are much larger, and then therefore you have much longer conductors and then therefore higher impedances. This also means that in urban areas, you have distribution transformers that are much bigger because they actually supply power to many houses simultaneously. And in rural areas, because there's less density, you have smaller transformers and they supply power to less houses per transformer. So all these differences means that we need to capture them in our analysis because any conclusions that we might do for urban networks might not apply to rural networks. So we will have those effects on the high voltage, but these effects will depend entirely on what type of networks there are. And in reality, there's not just urban or rural, there's semi-urban, long urban, small urban, so there's different types. So we need to really capture, you know, all these different types when assessing the hosting capacity for our networks. Now, a few definitions. When we talk about hosting capacity here, is really the maximum amount of electric vehicles that a given distribution network can actually host without negative effects, all right? So these negative effects are going to be, for this particular presentation, this report presented from the perspective of voltages, so within the statutory limits, and asset utilization or congestion of assets. There are many other things that can be quantified, but we are not going beyond that. And in terms of amount of electric vehicles, this will be the percentage of number of houses with a single electric vehicle. We will get into the details of that later on. Now, from a modeling perspective, of course, if we really want to capture all these voltages, all these asset congestion aspects, then we need models, right? And this is part of the challenge that we have around the world, having adequate models. Not that distribution companies do not have adequate models, they do for the high voltage part mostly, but the low voltage part is the one that is lacking, all right? Because of different challenges. So we needed to come up with some modeling techniques to really capture those interactions of end users, our houses, with the electricity grid. And I will explain that later. And all of that needs to be done in a way that the networks are really modeled in a three-phase unbalanced way. So we can capture the different relationship between the phases, okay? And done in a way that we can capture as well the changes in demand throughout the day and the changes of electric vehicles throughout the day as well. So all of this needs to be captured. The physics need to be captured, and this is very important. So let me move to that modeling that I'm talking about, demand and photovoltaics. Please remember there's a chat box there, that an option where you can actually place all your questions. So feel free to go ahead and place your questions. Do not wait until the very end. There will be time for us to answer those questions. All right, so this is an overview here of the different feeders that we have modeled in this particular project. There are 6 feeders, 4 of which have been modeled from scratch, and 2 of which were already modeled as part of a previous project. So the feeder from New South Wales, NSW, and Tassie, Tasmania, the TAS networks, are those that we have modeled, and the Victorian ones are those that have already been modeled. We capture the rural characteristics and the urban characteristics of networks, and this table really presents what we are doing here in a nutshell. You can see, there are networks with hundreds of customers or even thousands of customers. There are networks that are quite long and networks that are shorter than those distances. You can see here, for instance, the rural Victoria network is almost 500 kilometers in terms of conductors that are laid out there. So it's massive. So all of these characteristics mean, different challenges. Interesting to see as well the AD&D that was used to design the low voltage part of those networks as well. You can see that the AD&D, in New South Wales is much higher than the AD&D in Victoria, and the AD&D of the TAS networks is kind of in the middle. Now, all of this is just because the nature of the normal demand that we have in each region, but this also will affect how you have capacity, perhaps for extra demand, as you will see in the results as well. Important to see as well that in terms of photovoltaic penetration, we only captured the existing photovoltaic penetration for the New South Wales feeders, which around 20 to 30%, which is not small at all. We don't have photovoltaics, at least in the models, for the TAS networks and the Victorian networks. All right, let's move on. These are the networks in terms of their topology from the high voltage side, all right? You can see some of them look more complicated than others, as you would expect. For instance, the rural Victorian one is massive. The urban Victorian one as well is quite big, but in general, the networks are just, radial networks, right? Now, what we did, we used Dick Silent Power Factory and SynCal to then extract the corresponding port information and move it to OpenDSS, which is an open source platform, to do power flow analysis and many other type of analysis related to distribution networks. We created pseudo low voltage networks based on design principles used in Australia. So we eventually not only have the high voltage part, we also have the 3-phase feeders and the single phase conductors that connect each of the houses, single phase connected houses. So this allows us to really capture the voltages and all other challenges that we might see on the networks once we have a lot of electric vehicles. Now, the validation process that we use to really say, yes, our models are okay, is as follows. It's relatively simple to understand, I hope. And this all was done with actual data given by the companies. So we have Endeavour Energy from New South Wales, we have TAS Networks from Tassie. So this data was real data, historical data from the head of the high voltage feeder. So aggregated active and reactive power per phase. And we had it for some time, like a year. And what we did is we picked the peak demand day, all right, because that's the worst case scenario for electric vehicles. And we captured that particular day. And then what we did is we started using available residential profiles that we had for customers. For Victoria and for New South Wales, we were using anonymized smart meter data we had from another project from Victoria. From Task Networks, we were using a diversified profile that was provided by Task Networks as well. So we allocated that to the residential customers. Then we allocated as well PV profiles for those customers that have PV as well, so New South Wales in particular. And then we started tuning the demand profiles of C&I customers, which are commercial and industrial, to then try to match what is being seen at the head of the feeder. So we were doing the models running in OpenGSS and PowerFlows, trying to match what it is the SCADA data telling us. And we did a similar process as well with reactive power. Although with reactive power, we needed to assume as well a few things with the residential customers. But that is the process. So eventually, it's not a real network, okay? So remember, we have the the pseudo LV feeders, all this tuning. So they are not exactly as real, but they are as realistic as possible. And that's important so we can actually ensure that our conclusions are relevant, okay? Now, in terms of demand and the corresponding modeling that goes behind, as I was mentioning, for Victoria and New South Wales, we were using Victoria anonymized smart meter data from Victoria, and for Task Networks, we were using diversified profiles provided by Task Networks. Of course, you know, the moment that we use smart meter profiles, we are able to do this in a very granular way. So we are doing models that can allow us to do every 1 minute resolution profiles, but not just that, there's a lot of variability there as well because of the nature of the smart meter data. However, with the Task Networks diversified profiles, that are kind of average profiles, as you can see here in the slide, that granularity from the demand side is not that great. Nonetheless, very useful because of course the demand in Task Networks is much higher, as you can see in average, than what the smart meters show here in Victoria. And that is important to capture. So that's why we couldn't use the smart meter from Victoria in the Task Networks, because the demand is much smaller. As you can see here, you know, in Task Networks in average, you have for the urban Task Networks around 3.5 watt in average for the peak, and in Victoria you have around 2 kilowatts. So that difference is important because the moment that you put the electric vehicles on top of things can have a different impacts on the corresponding networks. So again, as I was mentioning earlier, we're trying to model things as realistically as possible. Now, I mentioned photovoltaics as well, only applicable to New South Wales, and the percentages are those that were given by Endeavour Energy, and the sizes as well, the average sizes were used as well according to the data provided by Endeavour Energy. We needed to use, of course, realistic profiles of generation, and what we did is just use clear sky irradiance, you know, from Melbourne that are quite aligned as well what can happen in New South Wales, very similar, and we pick, of course, the peak demand day that we are going to use for the models later on. Now, let's get into the interesting part. That was really the sort of building block, if you want to do this impact analysis of electric vehicles, the network models, their demand, whatever it is already happening today. On top of that, we need to put the electric vehicles, but first we need to have a modeling of those profiles of electric vehicles that we are going to use. Now, we in the report that is going to be publicly available, by the way, the report in many pages, so you will have time to go through that, but and it will be released in a few days. Anyways, there's a whole methodology to use the data, particularly from Electric Nation, which is a UK project that collected data from 2017 to 2018. The data is publicly available, although links are there. But the data, of course, is raw data. So we needed to analyze this data, define different charger sizes that they were using as well. We had to do our own considerations to capture multiple electric vehicles per house. We divided the data into subsets, weekdays, weekends, level 1, level 2 chargers, extracted probability distributions. You produce the binary profiles. Binary profiles are these 0 or 1 or on and off status of the charging. As you can see here in the slide on the right. Then we translated it into electric vehicle demand depending on the level 1 charger, you know, 3.7 kilowatts, or level 2 charger, 7.4 kilowatts. So these binary profiles are converted into actual demand profiles. And then you eventually end up with your electric vehicle demand profiles. And with that, you can actually then adapt these demand profiles for any specific considerations of having two cars per house, what would happen. I will explain that a little bit later. And finally, you also need to consider the fact that not all electric vehicles will be charging on the same day. All right, that's an interesting piece of information that sometimes is not used in this sort of models. I will explain what it means later. Finally, a power factor is needed as well, because it's not all about active power, it's active and reactive power, and this can have serious implications as well on the apparent power. And finally, how we consider electric vehicle penetration. So I'm going to go through all these steps that are important to understand, and then we will get into the actual results that we're going to present. So first step here is, okay, so as I was saying earlier, this is data from the UK. Is it applicable to Australia? It would be the first question, which is a very fair question to make. After analyzing it, it is largely applicable. Based on what we made that decision. Well, first of all, there's not much data around, all right? So we need to use something. And this data is extremely rich and is very real. So we assess the data and compare it to some statistics that we have here in Australia. So in terms of travel mileage, what we have here in Australia is around 200 something kilometers per week. In the UK trial, that was around 300 kilometers. You can argue that it's a little bit like not that close, but let's say it's not necessarily twice or three times different, all right? In terms of the plug-in time, Australian traffic decreases in general around the evening, as expected. People coming from commuting and from work to home, and that is also matching the data that we have from this particular trial. So again, another tick. And finally, the model diversity. This UK trial, it involved more than 700 cars from different makes. More details are in our report, and of course on the corresponding reports of that particular trial. But we are expecting, although we don't have many electric vehicles in Australia, not many even options, to buy electric vehicles from, that the market will catch up eventually. All right, and it's going to be very likely similar to the UK. So all in all, we decided that this set of data, not just because of its uniqueness, it's also relatively it's acceptable for the studies that we want to have here from a planning perspective, at least for Australia. Now, that said, then we needed to process that data to really make it useful for our studies. So first we needed to separate, the charger sizes. So level 1 and level 2 chargers, as I was mentioning, 3.7 and 7.4 kilowatts. Most of the electric vehicles are going to be having these level 2 chargers in this particular data. That is what is going to happen in the future anyway. So it's already the data was reflecting what we expect is going to happen in the future, because most people are going to install level 2 chargers. Now, when we have these different chargers, you have three options. If a house is going to have a second electric vehicle and you're using level 1 and level 1, that's okay, because 7 kilowatts might be acceptable to install. All right. Distribution companies will say okay, because it's not that much. Having one level 1 and level 2, that might still be acceptable, but having two level 2, which is 7 plus 7, 14 kilowatts, that is unlikely to be acceptable by distribution companies. So you cannot install that. So therefore, what it is a solution, I think a solution is today available, are dual-headed level 2 chargers, which is just two level 2 that automatically is actually halving the power if you have the two cars already charging simultaneously. So it would be 3.7 plus 3.7, or full charging if you just have one car. So those are the considerations that we are going to have the moment that we have multiple electric vehicles per house. Now, when we look at the data set as well, in terms of how do we actually create different pools of profiles, we noticed that around 96% of the electric vehicles, they will plug in, to charge up to twice a day. And that means, we don't need to model those that are going to plug 3, 4, 5 times. We also notice that weekdays and weekends have different behaviors, so it is worth separating them. And of course, naturally, the charging levels as well will have different behaviors, so level 1 and level 2. So we created all these different pools where we have weekdays and weekends, level 1 and level 2, and this is how we have our different pool of profiles. Now, these different profiles or data sets, if you want, then were analyzed in terms of the probability distributions. So we are able to actually, for a weekday level 1 electric vehicle charging, to plot all the corresponding distributions. As you can see here, people will have the charging time. If you're just charging once, it will be on the top left here in blue, that people will do it in the evening. Yes, as expected, after work. But your second time that you are going to plug in, perhaps is going to be a mix of throughout the day or in the morning and also in the evening, all right? And if it is the second one, up to two times that you are charging in the day, it's very likely to be in the evening. And for how long are you going to charge? Well, I mean, this will depend on different factors, but what you can see is 3-4 hours in general, up to 2 for sure in the most cases. And then the same thing can be done for weekdays level 2 charging. These are just examples. But once we have the probability distributions, it means that now we can actually produce profiles, because we can extract these distributions, and then with the start time and the duration, we can randomly select and combine to produce many, many profiles, 1-minute resolution profiles that can represent how people actually are going to use the electric vehicles at home. And this is very important. Now, the first profiles that we do are binaries, this on and off, all right? And then we multiply that by the corresponding charging level, we apply the charging level, and then suddenly we have many, many profiles, 1-minute resolution for the different subsets, weekdays, weekends, level 1 and level 2. So on the left here in the graph, you can see how these profiles work, So you have in different colors, different profiles, of level 2 up to 7.4 kilowatts, and level 1, 3.7, and how they are on and off during different times of the day. And these are the profiles that we're going to use then to run our power flow analysis. Now, just for you to see what it means, in terms of average demand of just the electric vehicle part, the plot on the right here, what it is showing you are the diversified EV profiles. This is an average of 1,200 profiles. So this is an average that you can say how my primary substation, my zone substation will be affected, the moment that hundreds of customers have electric vehicles. This is the value. But if you are looking at the low voltage circuit only, which of course you have less customers, that value will be a little bit larger, okay? But in any case, it's very useful to see here, because what we're seeing here is that during the weekdays, of course, we're expecting a larger demand in average. The coincidence is, or let's say the peak is around 7 p.m. to 9 p.m., all right, which is the coincidence as well, the peak demand that might happen in many networks that we have here in Australia. And also the fact that, a level 1 charger that has normally a demand of around 3.7 kilowatts, the moment that we have hundreds of electric vehicles charging, at different times, in average, that peak demand for a level 1 charging is around 1 kilowatt something. So a third. And for the level 2 is 2 kilowatts something, 2.2. And that is again approximately a third of the 7.4 kilowatts. So you can say, well, the coincidence is really 30%. Okay, still, even if it is 30%, with the moment that you have hundreds and hundreds of electric vehicles, can be significant. All right, and this is what we're going to discuss once we start presenting the overall results. Now, then we have, of course, the moment that we have the dual-headed level 2 charger, we have special considerations as well. And this gets tricky because these are two cars, level 2, in a single house. And we needed to do some adaptations there. But the most important thing is that, well, the corresponding aggregated demand might be much, much higher. And this can be a little bit worrying. However, of course, the moment that we see houses with 2 electric vehicles, it will take some time, all right? So perhaps not to worry too much in those particular cases. Then we have the charging coincidence factor in terms of the number of electric vehicles per day that will actually charge. Not everyone charges every day of the week, all right? That is what the data is telling us as well, and surveys are telling us. So what we have found is that it is more or less about 3 to 4 days of the week. That gives us more or less a coincidence factor of around 70%, for 99% of probability, all right? So what we're using is that even if you have, let's say, 100 vehicles, in a given day that you want to assess, only 70% of them will charge that day, all right? And this, again, helps us with a realistic estimation of the impact. Finally, we need to assume a power factor, and this power factor, well, based on, of course, measurements that have been done in other laboratory, it's around 0.99, is inductive or lagging power factor. And then, of course, in terms of penetrations, what we're going to look at is one electric vehicle per house up to 100%, and then beyond that, no more than 60% of the houses with 2 electric vehicles. So our penetrations will go from 0 to 100, and then 100 to 160%. All right, so those are the considerations. Now let's get into the results. This is the EV impact assessment on both urban and rural grids. So everything that I have presented in terms of the modeling of the electric vehicles and modeling that has been done for the New South Wales task networks and Victorian networks is going to go through a different process of simulations. And I will just pass this on to Will to continue. Thanks, Will.
Thank you, Nando. So yes, so we're moving into the EV impact side now. So we're focusing on urban and rural feeders, and we've seen earlier we've got 2 feeders from each region, so 6 feeders total. And we're really looking at, okay, what's the impact from unmanaged EVs on these networks, and importantly, what's the hosting capacity of these networks if we do nothing? And we've done our best to represent what is going on in reality. So let's get into it. So if we can move on to the next slide, please. So this is how we're approaching the EV impact analysis. So this is how we've got our networks. We've figured out how we're going to model the EVs. Now it's about combining the two. So first, of course, we want to set our EV penetration rate. So you can think of this list repeating for every EV penetration we're assessing. And as Nando said, we're doing this in steps of 20%. So up to 100%, we consider 1 EV per house. Beyond that, we then consider homes with 2 cars. And then what if that second car is also an EV, right? And about 60% of homes have 2 cars. So that's where that 160% comes from. And then importantly, we then want to allocate these EVs, and that's done randomly, both within the pseudo LV feeders. So as we saw in the topologies earlier, we saw lots of LV distribution transformers. So they're distributed randomly within those transformers, but also across the transformers as well. We then assign the demand profiles for the residential customers. We assign then charger sizes when we are assigning those EVs. And so, as we presented earlier, 80% level 2, 20% level 1. But of course, out of that penetration, we know that only 70% are likely to plug in that day. So you can think of that as a sort of a slightly lower penetration in reality. And then, of course, we want to assign the profiles for the EVs that were presented earlier. And the important thing there is, if you're assigned, if a house is assigned a level 2 and a level 1, that's no problem. You just assign the level 2 profile, the level 1 profile. But if we have a house that's now just had 1 level 2 charger, and then another EV penetration, it's assigned a second EV with a level 2 charger, then we need to replace both those profiles with the new profile that we were talking about earlier to then represent that behavior that we see in dual-headed level 2 chargers, where in particular we see that longer charger duration. Then, of course, we want to run the time series power flows. So this is a 24-hour simulation. We run it in 1-minute time steps. And then, of course, we want to look at the network, see what the impacts are. And this is, of course, repeated for every EV penetration. And of course, it's repeated for every network that we're analyzing. So we can move on to the next slide. So as an overview, we can think about, okay, well, what's happening with peak demands when we aggregate the whole HVLV network? And this already starts to give you a picture of where things are going. And importantly, what it means for the wider network beyond just the HVLV feeder. So we can see that if we compare here with this graph, what we're showing here is the increase of peak apparent power from the base case. So what is the increase of peak power from when we have no EVs? And we consider any time. So, just what is the peak at any time? And we compare that. And as we expect, peak demand is, of course, increasing quite significantly. For New South Wales feeders, it was between 80 to 100% increase in peak apparent power. TAS networks with the higher average residential demand in particular is a bit lower, 15 to 40%, and for the Vic feeders it's 50 to 110%. Now we're only modelling one HV feeder, for instance, where in reality connected to the zone substation, the primary substation, there might be several HV feeders. So when we talk about 80, 40, 50, 100% for one feeder's peak apparent power increase, this could potentially have significant consequences for the zone substation and other assets upstream when we then, well, what if all the HVLV feeders have this increase in power? So we're not modeling anything upstream. We can't model the direct impacts on the zone substations because, like I said, we're only modeling one of the several feeders. But you can already start to think that, oh, well, if all our feeders start having this increase in power, there could be some cause for concern there, and it's certainly something to think about. So if we move on to the next slide, please. So here before we sort of get into the results, this is sort of a summary of what's coming. And immediately you can see that there are problems. In particular, rural feeders are struggling to host even 20% of homes with an EV, whereas urban feeders tend to fare a bit better, but it really does depend on the region. In particular, that ADND that we're using to model the pseudo LV feeders, as well as the inherent residential demand in those LV feeders as well. So both of those factors really impact the urban feeder performances. But in general, urban is doing a bit better than rural, but we have problems, and we'll get into more what those problems are and what are those limiting factors that are preventing a higher hosting capacity for EVs. One last thing just to mention is the rural networks are actually using the slightly different voltage standard. So the New South Wales and Tasmanian are quantified using the Australian standard, and we'll touch on that when we go into the voltage plots, whereas the Victorian networks are quantified using the Victorian limits, which are a little bit wider. So instead of plus 10%, you have plus 13%. But importantly for EVs, instead of minus 6%, it's minus 10%. So that is something to note there. But nevertheless, we still have problems. So if we move to the next slide. So here we're looking at the impact on LV distribution transformers. The main takeaway here is that we have problems. Once we start getting beyond 40% and beyond, the overloads really start to become significant. There's a minor overload at 20%, but you could argue that's, within design ratings. Problems really start 40%. What you can also see is the overloads not only increase in severity for those that do overload, but the numbers of transformers start to really get quite significant once we get higher and higher. And in particular, once we get beyond that 100% mark, where we start considering the second cars that people have in their homes also as an EV, things really do start to get out of hand for the asset congestion. And this is absolutely something that would need to be addressed if we wanted to increase the hosting capacity. So significant problems at 40%. So we can conclude, based just on this asset, the hosting capacity is 20%. So if we move on to the next slide here. So here, I would also like to just highlight, we can see the effects of PVs in this. So the rural New South Wales feeder had 24% PV penetration. And if you look between, say, 10 in the morning to 2 p.m., you can see there's actually a slight voltage rise. And that's from the reverse power flows from the PV systems already modeled as part of the base case. Nevertheless, as EV penetration increases, we still get voltage problems despite that PV being there because it's at a different time. So of course, we're still going to get problems. Most people plug in their cars when the sun is set. So whilst there might be some mitigating factors, during the daylight hours, still have big problems. What we can see here is the red line there with showing the Australian standard, which is the one we're following for New South Wales. From 60%, we start having customers exceeding that. And the severity and frequency of these problems really starts to increase. However, when we talk about hosting capacity, really, you're talking about what's the bottleneck, what is limiting you from hosting more EVs. So yes, here we could host maybe 60% of EVs based on voltage, but we're still limited by that LV distribution transformer. So our hosting capacity is still 20% for this feeder. So if we move on to the next slide, please. So the LV conductors, again, it's a similar kind of story, except now the hosting capacity is higher. So the LV conductors, so these are the conductors within the LV feeders, not the HV feeder. These start to overload for this feeder for the New South Wales based on the ADMDs and demands we're using from 100% and beyond. Not quite as a significant problem as you saw, say, with the LV distribution transformers, but it's still problematic nevertheless. And again, we're still limited by essentially the lowest factor, right? So we're still limited by those LV distribution transformers overloading. So despite problems for the LV conductors at 100%, 80%, 100% and beyond, for this feeder, the hosting capacity would still be 20%. So for the HV conductors, it's getting better as we go through these impacts. We start seeing problems, significant problems at 140, 160%, whereas 120%, we see 1 or 2 lines with a slight overload. So we can just about say that's okay. But as before, the bottleneck is still those LV distribution transformers. So if we move on into the summary, we can see, yes, those LV distribution transformers are the real problem here. We can also see that by the maximum penetration, there's about 1 kilometre of HV lines that are congested. So that, if you have to replace that, that can be quite significant. And if we look at the LV distribution transformers again, we can look at just the scale of the problem once we start getting into those higher penetrations. So on the LV distribution transformers, we can see that by 100% of customers with an EV, over a quarter of the LV distribution transformers within this feeder are overloaded, and it's nearly half of the LV distribution transformers at the maximum penetration that are overloaded. So these are quite significant impacts. And if you're not going to go about doing anything about it, it's a lot to address to increase that EV hosting capacity. And finally, if we look at the customer non-compliance rate, which is the sort of second from the right, we can see that by the maximum EV penetration, approximately 1 in 5 customers have a voltage issue as well. So these are quite significant impacts, quite significant numbers, but of course this is just one feeder. So if we move on to the next one, please. So here now we're looking at New South Wales again, but the urban feeder. We've got a slightly higher PV penetration installed capacity, but we can see the impacts, particularly for these LV distribution transformers for this feeder, are much different. So here, we're at the maximum EV penetration, we only have 1 transformer overloading. So that is the limit of our hosting capacity there. And it's slightly overloading, so you could argue, yeah, no more than 160%, that's our limit. So yeah, we can already see there's a vast difference between feeders already, as we're starting to see. And we move into the customer voltages. Again, you can see that voltage rise during those daylight hours. You can see that bump there. And this is higher with a higher PV penetration and PV size. And again, we can see the voltage dropping as EV increases, but we don't actually exceed the limit. So we could say, yeah, the hosting capacity is also 160%. But an important thing to note here is, yes, we might not have any problems, but you'll notice if you look at that 160% plot on the bottom right, we're very close to both the upper and lower voltage limits. So let's say PV is to grow in penetration, you're then going to start running into problems in the upper voltage limit. And then you can't really do much adjustment with the offload tap positions of the LV distribution transformers to lower the voltages, because then you're going to exceed the voltage limits in the evening. So while there aren't voltage problems here and the urban feeder is doing well, it's something to think about certainly going forwards. So if we move on to the next slide, please. The LV conductors, again, problems start at 100% and beyond, and the hosting capacity is 80%. Similar kind of picture as we saw with the other feeder. And if we move on to the HV conductors, we can see that for this feeder, there's no problems at any EV penetration. So for the urban New South Wales feeder, that bottleneck we were talking about, that limiting factor that determines the hosting capacity, means that we are still at 80%. And if we move into the summary, we'll be able to see this a little bit better. So firstly, the LV distribution transformers, that 1 transformer overloading, yes, that's an issue, but the real issue for this feeder is those LV conductors that start to overload at 100%, whilst we have no problems in the length of the feeder for the HV feeder. and we have no problems for customers. So the final hosted capacity is 80% for this feeder, and we see the LV conductors are that real bottleneck. So now if we move on to the next slide. So here, in the interest of time, we're just going to be presenting the summaries for the remaining feeders. So for the rural Tasmania feeder, we can see that here as well, the LV conductors are the bottleneck, with problems occurring at 40%. So the hosting capacity is just 20% for the rural Tasmanian feeder. And we can see approximately 1 in 10 customers start to have voltage problems when we consider the maximum EV penetration. However, the HV feeder doesn't overload us all. And finally, the LV distribution transformers, once we get beyond 100%, over 1 in 4 of the LV transformers start to overload. So these are all quite significant numbers of assets that are all becoming problematic. So if we move on to the next slide, to the urban Tasmanian, it's a similar kind of picture. The LV conductors are again the limiting factor, this time at a slightly lower penetration with that higher average demand and likely higher number of customers. LV distribution transformers start to overload at 80%, and by 100%, a quarter of those transformers are having issues, which is very significant. However, with this urban feeder, we don't have any voltage issues, but we do have HV feeder congestion issues from as early as 40%, and by 160%, that's over 1.2 kilometers of total congested HV lines that are problematic. So again, LV conductors are the bottleneck here. So if we move on to the Victorian feeders, we can see that the LV distribution transformers are the first bottleneck at 20%. We also have customer voltage issues, and we also have HV conductor issues. So this very long feeder really has a lot of limiting factors, all at 20%, that must be addressed. But the hosting capacity is 20%, and at the maximum EV penetration, again, it's about, as we saw with the other rural feeder, it's about 1 in 5 customers with a voltage issue. So this is very significant. If we look at length of congestion for this feeder, much larger numbers because we have a much larger feeder, but in percentage wise, it's usually around that sort of 5–10% mark of total length. Still very significant. So if we move finally onto the urban Vic, we can see that we have a similar EV hosting capacity, but the problems we have are not quite as widespread. Here we have a few LV distribution transformers overloading, but by 60% EV penetration, we have about a quarter of those transformers already overloaded. So that's very significant. This is quite a large feeder. So we're talking about quite a lot of transformers there. Whereas the LV conductors start to overload at 80%. We have minor voltage problems, particularly once we go beyond 80%. But we still have that HV conductor congestion issue with over 3.5 kilometers congested. So if we move on to the next slide here, we can see a summary of what we were discussing here. The green text is showing everything, is showing, yeah, those values are within limits. So if we look at, say, voltage, green voltages are good, red voltages, things are significantly exceeding the limits. And then the yellow is where we have those borderline cases where it's slightly exceeding the limit, but you could argue it's within the design ratings. What are the key takeaways here? Well, firstly, we can see that asset congestion is the main issue. That's really the limiting factor for a lot of these feeders, particularly the urban feeders that can be very problematic. The second thing is voltage issues in the rural feeders can be quite significant, whereas particularly for let's say the majority of our urban feeders, there are no voltage issues, and the one urban feeder there was a voltage issue. It's quite a minor thing. So voltages in urban feeders are good, rural feeders can be problematic. And finally, LV conductor congestion can vary between region, and this is mainly on the AD&D that we use to design those LV feeders, but also the inherent residential loading of that region. So Tasmania has a higher loading coupled with a lower AD&D. We're going to see some problems there based on the conductors that we use. So that's where I hand it back to Nando, and thank you for listening. Cheers.
Thank you very much, Will. And just to finalize, and then I can go through some of the questions that are already there in the chat. Well, electric vehicle impacts will vary, and that was the whole point of this analysis here. It will vary depending on the type of network and the typical demand for which that network has been designed. Also, it's important to say that this is not just about the residential demand. Each network that we have modeled have different proportions of non-residential demand, and that can also affect things, because if you have a large demand that is coming from non-residential, and then you assess, this tiny, even if it's a high penetration of electric vehicles, but it's just a tiny number of residential customers, of course, the effect is not going to be that significant. So it all depends on that as well. Now, of course, the larger the ADMD values that are being used to design the networks, such as in New South Wales or Tassie, of course, their ability to handle higher EV penetrations is going to be better. Rural grids, as already mentioned by Will, have a very hosting capacity up to 40%. It's not to generalize, it's just to show you what we have modeled. This cannot really be generalized. What can be generalized, however, is that definitely there will be asset congestion issues, and the transformers are really affected very quickly, which is similar as well to urban grids. However, depending on the urban grid, you can even have a much higher EV hosting capacity. Asset congestion is definitely a predominant factor here, but voltage issues can happen. The problem here is that so far we haven't really modeled significant penetrations of photovoltaics. Now, when we handle photovoltaics, normally we would change the off-load changers, to reduce the voltages of the transformation of the ratio, so we can handle voltage rise. But the problem is that if we have those effects or those mitigation strategies in place, then that will exacerbate the problems with electric vehicles as well later at night. So the moment that we start incorporating different penetration of photovoltaics, we will see that the problem is even higher or a little bit more complex than what we are presenting today. Anyways, given the amount of time that we have left, this is where I finish. We will provide all these slides and corresponding links as well to all the different information. I just want to thank ENA, C4Net, API, and the University of Melbourne as well. All the people involved in the project as well that have helped in different ways. And as well, Jean from the University of Melbourne for all the support in the modeling. And now we move into the questions super quick. Let me try to answer some of them, at least for now. Time of discharge, well, no, electric vehicles are not discharging here because this is not V2G, this is just charging. But yes, the time of charge matters, as we were presenting in the models. You need to model that adequately. What else? The question, yeah. Anything else? Presentation, SWER systems. So this is a question here about the SWER systems. There are SWER systems in some of the networks that we have modeled here. The actual modeling that we have done is to sort of resemble SWER, but hasn't been detailed to really capture SWER. Nonetheless, the effects are being captured to some extent. And definitely, these rural networks, as it could be seen here, they are affected very quickly, but not so much in terms of their voltage, because the rural networks are geared up, for voltages really. So their effects are really more with photovoltaics, but in terms of the assets, the little transformers very quickly, and the corresponding conductors as well, in the LV and the high voltage, they get congested as it was presented. What is the difference between solid lights and dotted lights on slide 6? Darren, that is between weekends and weekdays, I believe. You will see the details in the report and the slides as well. EV profiles and charger sizes assigned randomly, wouldn't that lead to unexpected combinations? Yes, that is correct. So this was this in reality how you have to do this assessment properly, but the problem is that we don't have really the amount of time to really do it in that way, is to do it in a stochastic way. So everything that we have presented there, as much as there's a random allocation of demand and electric vehicles, yes, we can have a scenario where all the electric vehicles were placed in the houses that are at the very end of the high voltage feeder and the corresponding low voltage circuits, and then therefore the impacts are going to be, from a voltage perspective, much higher than if they were allocated somewhere else, correct? So in that sense, that is correct for sure. And then therefore that's why you need to do it in a Monte Carlo way, for instance, multiple scenarios, and then capture all the results from all the different scenarios. We haven't done the Monte Carlo approach here just because of time limitations, but that's what I would recommend. Nonetheless, the thermal aspects, well, that wouldn't affect so much. They will be very similar. And given that what we are capturing here is that the thermal aspects, the thermal issues are the most predominant factor, then I think that the results are going to be, let's say, very, they are going to mimic very likely any Monte Carlo assessment that it is done. Anything else here? There's a question here about diversity spread among EVs. Well, as I was mentioning, Peter, in one of the slides, what we are seeing the moment you have hundreds and hundreds of electric vehicles, it is around 30% of that demand. So 30% of say 7.4 or 30% of 3.7 if it's level 1. Nonetheless, that is when you have hundreds. For a distribution transformer, you will have dozens. So it means that that 30% that I'm mentioning doesn't work. It will be higher. So we can do the assessment. We haven't done it yet, but it will be higher than that for instance, between 30 and 50% for sure. But it will not be like adding, all the level 2 or level 1 charges, for sure not, because there is diversity, which is great, of course. And that's what we were expecting. What are we? When are we expected to reach this penetration? That's a great question, David. That depends. There are many. I would recommend in our previous report we had a link to and we also presented as well the trends according to what CSIRO has projected for electric vehicles in Australia. Forecast, I mean, if we trusted the forecast, we would be rich. They never work, but they are an indication, and that can take some time really to have really high penetrations here in Australia. But things can change depending on different incentives that we might have in the near future. So that's why we focus on the different penetrations rather than the years and the trends, because these trends can actually change dramatically. There are other questions. David, please let me know about the time. I know that I'm already exceeding 2 minutes above the 1:30 p.m. that we promised. So just let me know when I need to stop because there are a few more questions.
Yeah, Nando, I think just proceed as you need, and people can exit if they need to, knowing that we've got the recording of the webinar.
Excellent. All right.
So I will jump in later.
I will go a few more minutes then just to answer these questions. Well, continue here. There's another question from David. To refresh on the generation and shift for a customer to say that like to shift location from.
Just to clarify, Nando, those questions that appear to be from me are actually, so people that use the link I shared to access the webinar, they're all appearing as me. It's not me. They're actual direct questions from individuals. So, yeah.
Oh, it's a very interesting question from this David Tester. All right. So there's another question here about the generation and the solar generation and electric vehicles. So this is a very interesting question. So for this particular report and this analysis, we haven't really captured all the different effects or synergies, if you want, that we might have with photovoltaics. Yes, we capture the current penetration that we had in terms of photovoltaics for the New South Wales feeders, the rural and the urban, around 24 to 30%, which is not small at all. It's significant. And we could see already, a very nice synergy in terms of some hours. The more photovoltaics that you're going to have, the more you're going to see that synergy, and the less the effects of electric vehicles on the networks for those hours. But the reality is, as you guys could see, and this is very important, let me just go to that average profiles that we presented of the electric vehicles models here. I think that this is more important. Is that the coincidence, the largest coincidence of electric vehicle charging happens at around 7 p.m., 8 p.m. So doesn't matter how much photovoltaics you have, the synergy will not help there because you don't have light, period. That's it. Oh, you might have a little bit in certain northern states. Yes, that's true. But still, you don't have as much. It will be what? Even if you have all houses with photovoltaics, the irradiance is enough just to power, I don't know, around 10, 15% of the installed capacity. So the reality is that the synergy with photovoltaics and electric vehicles is not significant, unfortunately. It will help in terms of energy, who generates, etc. Yes, but from the network perspective, in terms of the power flows, it will not help. Now, what happens if these people that have solar photovoltaics start using batteries? That's another story. That's another story that we will investigate, of course, for the next part of the project. And that is really the holy grail, if you want, because then you move, the electricity that you would be exporting. Now you store it in your battery, and then you use the battery to actually charge your electric vehicle. That would be a win-win situation for the end user, at home, and also the grid. Now, batteries are very expensive still, but that might make sense in the near future. So that is an interesting proposition that we will investigate for sure. Then we're moving to the basis for 20% level 1 charging installations. For the basis for that is that the trends, there are references that we have in the report as well. So I encourage you to go to that report. The person that was asking about this 20% level 1 charger is that most people will eventually adopt level 2 chargers. So that's the trend internationally. Why? Because it's more power. You don't want to wait so many hours, with your electric vehicle charging. So everyone that can actually adopt the level 2 charger or the 7.4 kilowatts will go for that. All right, that is what is going to happen.
If I could
Yes,
interject that the actual data we have currently, as of what it was 2018, it was 60% level 2, 40% level 1. So as Nando said, we expect many more level 2 chargers to be installed. So another 20% in the coming years, I think it's quite reasonable. Sorry, back to you.
Thanks, Will. There's another question about the networks may be able to host certain penetration and low will remove significant amount of spare capacity. That's correct. Yes, understanding all these impacts are important. That's what we're trying to do, Will, Arlington here. Then there's another question from Robert. Yes, AGL EV orchestration trial. Yes, that's correct. We are keeping an eye on that particular project. Definitely, we will try to model some of the management strategies that are being investigated in that trial. Thanks for pointing that out, Robert. And definitely, this is the next stage of this particular study, because then we can actually mix those management strategies with the effects on end customers and the effects on the grid, and try to see what works best. So yes, we will be analyzing those reports from this AGL EV orchestration trial in more detail. Thanks for that, Robert. Frank is development of blockchain techniques into the low and high voltage systems. I'm not entirely sure about that, Frank. This is just simple adoption of a technology without management, so business as usual, so no blockchain. Now we have another question from Will. Variability in different types of networks. Urban networks don't have same characteristics for it. That's correct. Well, I mean, the diversity in terms of electric vehicles, eventually each region will have its own diversity. What we were trying to show here is what has been found so far in the trial of the UK, and to some extent might be applicable to Australia. In reality, how people will use it here in Australia, well, it's yet to be seen, really great numbers. And then we will learn about that. But the comment from Will Tarlito here in terms of the diversity also of the networks, yes, that's what we try to really show here. The diversity is massive, is significant. So as much as we are trying to say urban and rural, it is not that. The spectrum can be very big, even among urban networks and rural networks. And that's why DNSPs know this very well. You don't silo them in just two groups. You can have multiple groups indeed. So yes, I mean, at some point, this analysis needs to be actually more refined for the different characteristics of the networks within each DNSP. Are voltage issues reduced with three-phase charging? That's a great point, Peter. I believe so. Voltage issues will be reduced with three-phase charging, and the reason for that is that unbalance plays a role here. Everything that we have done here are with single-phase connections, and that has the chances of increasing balance. If you have three-phase charging, it means that it will be balanced among the three phases, and that will have lower impacts. We know that for sure. We know that we already with solar photovoltaics, so the same thing will happen with electric vehicles. Now, you cannot suddenly, change the single-phase connection of houses to three-phase, though. That's a challenge there. Now, Paul is making a question: multi-phase and single-phase chargers. Do you want to know? Only single-phase connections. All of them are single-phase connections here, Paul. And you're right, balancing the load will make an impact for sure. But again, my point being is, if houses are single-phase connections, how suddenly they are going to have three-phase chargers? That would be a dedicated installation, and that creates other challenges, I believe. However, it's not something to be dismissed, because it could be an option for the future, of course. Renewable systems, I already mentioned photovoltaics. Joseph Tadish. Oh, Joseph, thanks for joining. We have EV propulsion charging once connected. Industry moving towards price reflective. Yes. So we haven't really captured price reflective tariff, Joseph. That's a fair point. As a matter of fact, the UK trial has the data of the charging once tariffs are affected or incentive for customers to shift their demand are in place. We removed that because the idea here was to do an analysis of business as usual. So kind of worst case scenario, if we don't do anything, what will happen? That is the stage of that project right now. The next stage is to investigate management strategies such as what was mentioned about the AGL EV orchestration trial, and also tariffs as well. So we will be investigating the effects on tariffs as well, for sure, Joseph. That's very important. For the most existing conditions, restriction transmission system. No, what it would be the effects on the higher voltages? We haven't done that, Shiva. That's just too much work. That might require another project. And sort of short time overloading of the transformer. Oh, that's a great point. Okay, that's David moving the question. Yes. So one thing that is very important is that we haven't used the cyclic ratings of transformers or conductors. So we have just used the normal ratings, of the corresponding season of the peak days, so the summer rating or the winter rating. But transformers have cyclic ratings as well that they can withhold easily, 10 or 20%, depending on what each DNSP uses. So we try not to use that just to sort of demonstrate, the extent of the effects. But definitely, that's something that eventually the decision makers within DNSPs need to consider. So yes, that's a good point to raise. And I think just based on the time as well, David, perhaps we should finish right now, just not to extend the discussion so much. Thank you very much for all the questions, by the way.
Great work, Nando. Thank you very much. And thank you to Will and the team and everyone else. And as you said, thanks to ENA and C4Net for their help in bringing this all together. So as we wrap up, as we've said, I've put in the chat, but we will send information out to you that the slides and the webinar will be available online for you to access later. The previous two webinars are also available through the C4Net website, sitting up on YouTube, and the slide decks are available as well. So thank you, everyone, and thank you again, Nando. Great work, and we look forward to more progress in this great project. So thank you.
Thank you very much.
See you later, everyone.